On March 3rd at Izu Atagawa, while doing some deep sky imaging, I also set up my Canon EOS R8 camera on a stationary tripod and pointed it at the sky. The deep sky imaging experience was described in episode 32 of Astrophotography Japan, published several weeks ago. In this video, I will focus on the Canon R8 camera images. That night, on March 3rd, I captured about 90 minutes of image data using a 35mm Canon RF lens. The field of view covered from just above the horizon to about 50 degrees of altitude in the southern sky. Being Bortle Class 4 in that area, the 10-second exposures revealed hundreds of stars and their sidereal movement across the sky when viewed in time-lapse. But when I closely examined the time-lapse footage, I noticed something peculiar. Near the top and center of the field of view, there appeared to be a flare of brightness in one location that did not track with the sidereal movement of the stars. You can see this best on the zoom image shown at the right. Notice it appears to remain stationary in the field of view, and the flare actually lasts for quite a long time. Then later, toward the end of the time-lapse movie footage, further to the right, another flare appears in the last few frames. It too also remains stationary with respect to the framed image. Throughout that time-lapse movie footage, there were clearly streaks of light from airplanes headed to some local airport, and even multiple satellites visible as faint dots of illumination, transversing the field of view in straight lines, as one would expect from orbiting objects. On other nights, at other times, with just my eyes, I have seen flares of light in the night sky that lasted a few seconds and disappeared. This is not uncommon around sunset, but what I saw in this video was different from all of that just described. It was stationary, it flared for a long time, many minutes, and it occurred hours after sunset. So I was a bit baffled and I wanted to investigate. Firstly, on this slide is a table of information relating to the 10-second still images that showed the two flares. The first flare was visible in about 40 frames. Combined, that had a total elapsed time of nearly 14 minutes. And the second flare was seen in the final 9 frames. So I do not know how long it would have lasted, but it was equally as bright. Of all the images, I selected 3 intermediate frames, outlined them in yellow here, and displayed them on the next slide. The frames all have the same field of view. Remember, the camera was on a stationary tripod. The left edges are all exactly aligned, and there are about 100 seconds of time elapsed between each of these images. You can thus see the sidereal movement of the stars toward the right in the field of view, and also the stationary positioning of the flare as marked by the vertical red line. It peaked in brightness at about the middle frame, number 4623. Here it is shown in the full frame image and a zoomed image of that particular frame. Interestingly, just to the right of it are a grouping of bluish-colored stars that appear to be a cluster. I identified this object in Stellarium as the M48 open star cluster. Furthermore, I also labeled a couple of bright stars in the zoomed image as well. These 2 stars appeared to be around magnitude 4, and the flare was a bit brighter than that, perhaps around magnitude 3. So it would have been visible to my eyes if I happened to be looking in that direction at that particular time. The star 28 Mon is part of the constellation Monoceros, and the HYA star is in the constellation of Hydra. This is an annotated copy of my image after analysis by the online resource of astrometry.net. As you can see, if you program Stellarium with the exact specifications for the Canon EOS R8 sensor and 35mm lens, the predicted field of view is almost identical to my actual image. Not perfect, but very close. Near to the top, you can also see the location of the M48 open star cluster in the Stellarium simulation as well. Also notice the yellow line that I included in the Stellarium image. That is the position of the celestial equator when viewed from my latitude here in Japan, which at Izu Atagawa was 34.8 degrees north at that time. This means that the interesting flares were seen close to the celestial equator, in fact just a few degrees below it. This is an important point. I want to give you another look at that video image, this time with a higher degree of zoom. Because if you look closely, there were actually 3 more very dim objects located nearby that also appeared to be stationary, and they did not flare. Take a close look. It was the location of these objects close to the celestial equator that provided the strongest clue to their identity. According to an article written by Bob King in the September 2017 Sky and Telescope magazine, a belt of geosynchronous satellites in orbit above the Earth's equator would appear to be about 6 degrees lower in declination when viewed from 35 degrees north latitude. I surmise that this specific position must have something to do with our vantage point, the height of the satellites, and the angle of our viewing from the Earth's surface. As you can see in this slide, the M48 cluster, which was located right next to the flare, is exactly 6 degrees below the celestial equator where I took these pictures in Japan. Exactly. Based on their stationary nature and location, I think there is no question these are some kind of satellites, probably geostationary. These satellites are generally located very high above the Earth's surface, usually around 36,000 kilometers or 22,000 miles high, and take 24 hours to complete one orbit, matching the rotation speed of the planet. By comparison, the ISS orbits at only 408 kilometers, or approximately 1% of that height. Geostationary satellites, like all others, will flare if and when their solar panels become positioned exactly right to reflect the sunlight down on your viewing location. So I believe this small mystery is solved, but of course I wanted to explore it more deeply to verify it further, just because I am a curious nerd. Several weeks later, on April 10th, from my backyard in Yokohama, I tried to repeat the imaging of this area of the sky at a slightly higher focal length. But I soon learned that identifying the location was not so straightforward. The original images on March 3rd were taken with my Canon R8 camera, and at that time, as you saw, the specific satellites captured were close to the M48 cluster. But the second imaging run was more than a month later on April 10th. The movement of the Earth had progressed significantly along its orbital path around the Sun, whereas these satellites are essentially docked in one location above the Earth's surface. In fact, M48 passes by these satellites almost 2 hours earlier on April 10th. To find these satellites again, we would have to look at the same location in the sky relative to the Earth's surface. This means we need to reference altitude and azimuth coordinates. So if we go back to Stellarium and look closely at the data again, we can identify the alt-az coordinates of the flare location. The little circle in the center is on an arbitrary, very dim magnitude 13.8 star that is precisely where the satellite flare happened previously. The alt-az coordinates of that star are given in the upper left corner and marked by the yellow arrow. However, the April 10th follow-up images were to be taken at my home in Yokohama, whereas the original photos were taken in Izu Atagawa, about 43 minutes of latitude south and 29 minutes of longitude away to the west. Okay, well, I can compensate for that too, but in wide field views encompassing several degrees of sky, that geographical difference may not have too much of an impact. Still, it seems simple, doesn't it? Just point the telescope at those alt-az coordinates and take some photos, right? No, not so simple. Because like many of you, I use the ASI Air computer to navigate the sky, and its go-to function only works with DEC and RA coordinates, not alt-az geographical coordinates. So to use the go-to function, I would need to convert from alt-az to DEC and RA. This would require careful planning of a precise time of the imaging session in advance. Actually, it is possible to do this in Stellarium by advancing the simulation time to the planned imaging date and time, shown on the right here, and then cleverly searching the celestial map for the Alt-Az coordinates. Once you find those sky coordinates, you can note the corresponding instantaneous Decan RA coordinates of that same celestial location. It is cumbersome, but it works. This slide shows the celestial data of the objects on March 3rd on the left and the new celestial data on April 10th on the right. The Alt-Az coordinates are closely matched and therefore identifying the same stationary position in the night sky, but the Dec RA coordinates are clearly different due to the passage of time. There is also another way to get at this conversion data. Remember, the point here is to find corresponding coordinates on the celestial sphere and enter into the ASI error for the automated go-to action. I found some online conversion applications on the Clear Sky Tonight web pages. It requires the use of two algorithms sequentially. The first is the horizon to equatorial algorithm. Shown here, when I entered my Alt-Az data, it gave me a declination coordinate and something called an hour angle. Although I do not conceptually understand the hour angle numerical value, it can be used to get the right ascension coordinate in a second algorithm, the hour angle to right ascension algorithm. In this second step, additional entered details convert the hour angle to the proper RA coordinate at the exact time and date and place. Hence, on April 10th, at exactly 3 o'clock in the morning, I had proper RA and Dec values to program into my ASI Air computer to salute to the exact same area of sky where I previously saw the potentially geostationary satellites. Now, if you are observant, you may have noted that the RA and Dec coordinates calculated by these two methods are not exactly the same, but they are very close. There are reasons for this discrepancy, but honestly, it's not worth explaining here. I have chosen to ignore some small variables and differences because their impact on the results cause only a few arc minutes of error. Well, to make a long story short, my attempts to image the same satellites from my home location with a 50mm camera lens were unsuccessful. Although I found the same position in the sky, approximately 6 degrees below the celestial equator, I could not identify any luminous stationary objects in the photographs, and I did not see any flaring. Bummer. I'm guessing there are two possible explanations for my failure to confirm these objects. One, the satellites are still there, but their position and angle of incidence relative to me and the sun has changed. Hence, they were no longer reflective enough to be seen with that particular lens and camera. Remember, these satellites are quite far away, nearly 36,000 kilometers, and would consequently be very small and dim, especially given the high levels of light pollution here in Yokohama at Bortle class 7 to 8. Or two, these satellites are not really geostationary satellites, but rather geosynchronous satellites. Interestingly, geosynchronous satellites are similar, but different, in that geosynchronous wander a bit in a figure-8 pattern with regard to latitude and longitude, but they do have an anchor point somewhere with respect to the Earth below. I borrowed this video that you are watching now to show the difference between these two types of synchronized orbital satellites. To be honest, I do not exactly know why I could not relocate the satellites I identified that night in March at the Izu location, but I am not one to give up easily. So I did take another trip to Izu Atagawa about a month later to look again, and I found them. And you can check out those interesting results along with some other beautiful sea star images in Astrophotography Japan episode 34, the next follow-on video. I hope you watch it. It is interesting that the sky above us on one hand is apparently unchanging over eons of time, But that is an illusion due to vast distances of deep sky objects and very tiny angular shifts barely detectable with only the most sensitive and sophisticated professional instruments. On the other hand, the sky is also dynamic, with movement of comets, planets, moons, asteroids, the appearance and disappearance of novae and supernovae, and other natural phenomena that can be observed by amateur stargazers like me. In addition, we also have thousands of man-made satellites and rockets and space debris that appear most unexpectedly and unwantedly in our astrophotographs. I find it all fascinating, and once in a while enjoy the detective work and research required to identify and understand these interesting little anomalies. Ain't science grand? Thanks for watching. Here in Yokohama, I'm JP Astro Guy. My name is Paul Cheesegel, and you have been watching Astrophotography Japan.